Okay, so let's go through this one. So for this problem, the coordinate system's over here. And so let's just start thinking about, like, we know all the things that are going to go into the equation for a rotating coordinate system. So let's start thinking about what those are. The coordinate system is rotating with body one, right? So what's the capital omega going to be? It's rotating about the y-axis. You know, this axis here that it's rotating around is parallel to y. And the right-hand rule says that it's in the positive y direction. So this is going to be 0, 10, 0. What about... I think I might have even said this in this same way before, but this axis, so if the coordinate system wasn't rotating at all, this axis would be in the positive y direction, right? Why doesn't the fact that it's rotating affect that?
Because the other two axes.
Well, so it has to do with the type of rotation. So if it wasn't rotating, you know, its axis here, this axle, is pointing in the plus y direction. When something rotates, the axis it's rotating around is the only, that's the only set of points on the body that doesn't change location, right? So even though other things are changing, the direction of x and the direction of z, those directions are changing. As this thing rotates, its y-axis stays exactly where it is. That's a property of the axis of rotation. And so that's why our intuition about what's going on if it wasn't rotating still works in the rotating case. What's omega dot? 0, because it's constant. Yep. And now, what does the position vector look like that we care about? So before we put numbers to it, where does it start and where does it go to? That's right. So that's what a position vector is. A position vector goes from the origin to the point that you care about. Okay, so this blue is our position vector. So P is equal to positive 2 and then negative 1y, 0z. Okay. What about the components dot? Yeah, so first of all, and this is something that people get confused about all the time. If you take the derivative of 2, negative 1, 0, you get a vector 0, 0, 0. But that's not the right thing in this case. Why can't you do that here? That's right. This isn't representing the position over time. This is just representing the position at a single instant in time. Okay? So if the position was constant here, then yeah, that would be fine, and the observed velocity would be 0, 0, 0. But there is some function, you know, because this position is changing over time. You just don't know what it is. So you have to find the observed velocity a different way than taking the derivative. Okay, so the components dot. You get that as lowercase omega crossed with r. So what's the r vector now? Let's draw the r vector in here. Right. It's from, so for somebody observing this motion, somebody fixed on this red coordinate system, observing this motion, all they see is a circular motion, right? And that circular motion has its center of rotation here and the point of interest here. So this is the R vector, okay? Also, don't, okay, so if you calculate this, our omega is negative 20,0, yep. And our R vector is 0, negative 1, 0. And because the axis is, you can see that the axis is parallel to X. And then it's rotating, it's coming out here into the page on the top. So that's a rotation like this. So that's a negative X. And so you get an observed velocity of 0, 0, positive 20. Does that direction make sense for the velocity? Yeah, I mean, so an observer rotating with this coordinate system is just seeing this circular motion. And at this instant, that thing's going tangent to its circular path out of the page. So that's a positive Z velocity. And one thing I want to point out here is, notice that, so why do I keep writing components dot instead of just saying, wouldn't it be easier to just say P dot? It's different, yeah. P dot is the actual true velocity, you know. P dot is equal to the components dot plus omega cross P. Okay, so these are not the same thing. This is the one we want. This we don't know. So that's sort of an aside. And then what about the components double dot? What equation do we use to find the components double dot? Watermelon equation, because again, the observer on that coordinate system just sees this circular motion. Okay, so that's equal to, so yeah, watermelon. So we have no, okay, so right, no angular acceleration. And then the centripetal acceleration is negative 20, 0, 0. Crossed with the quantity negative 20, 0, 0, 0, negative 1, 0. We already figured out that part, so. This, and you end up with 0, 400, 0. Does that make intuitive sense? Yeah, because that's a centripetal acceleration, and so it should be pointing from the chosen point up toward the center. That's in the positive y direction. All right, so now we have all the pieces we need. So the acceleration of that P is equal to, so it's components double dot plus omega dot cross P plus 2 omega cross components dot plus omega cross quantity omega cross P. And so that is, we've already calculated all these. So 0, 400, 0 plus 0 for this one. This one is, so we have 2 times 0, 10, 0 crossed with 0, 0, 20 plus 0, 10, 0 crossed with 0, 10, 0 cross 2, negative 1, 0. Add that all up and you get 200, 400, 0. And what are the units? Yep.
Why is the positive? Shouldn't it be coming towards the center?
The angular accelerate. So you're right about that. That centripetal component is. So your intuition is telling you about that centripetal component. But what your intuition is not telling you about is the Coriolis, that weird Coriolis term that in this case is a big positive X contribution. So this thing that you don't have intuition about is counteracting that. Right. Right. But positive 400 Coriolis. Yeah, right. Okay, and then we want to calculate the force applied to that mass by the bar. The mass, it's 5 kilograms, so we have a weight down of 49.05, and then some unknown force vector provided by the bar. And so Newton's second law says the force provided by the bar plus the weight is equal to the mass times the acceleration we just calculated. And so the force applied to the mass by the bar is 1,000 newtons and 2,049 newtons. Right. That's right. Yeah, if you came up with those position, yeah, in this case, it wouldn't be that hard, I guess, because you could come up with a position vector in terms of, so the position vector as a function of time would be 2, and then like 1 times, and then in the y and z plane, you'd have cosine and function of cosine and sine. And so those are things you could, take your derivatives of and stuff. Yeah, in this case, you could probably do that without too much trouble. But it gets a bit messy usually. All right, so let's do the second part. Can I see that really quick? Yes. I guess why don't you work on the second part for 10 or 15 minutes, and then I'll do it. And so then we're not going to talk about the work energy principle at all. It's in the old notes. If you want it, you can go to the lectures. So it's on D2L. So if you're making a notebook or anything, you might want to print those out and put it in there for future reference. But we'll just finish this for today.